Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. I have Adam Feinberg. He's an associate professor at Carnegie Mellon University. He's a member of both the Next Manufacturing Center and the Bioengineered Organs Initiative at CMU, Carnegie Mellon. So, Adam, thanks for coming.
Yeah, great. Happy to be here. Thanks for the opportunity.
Yeah, so, it's probably obvious, but why are you working on bioengineered organs? What particularly do you want to accomplish by creating them, and which organs?
Yeah, well, as you mentioned, I think it's pretty clear that, organ failure is a really, big healthcare problem. Most causes of death are ultimately due to organ failure, and there's really just very few options for people. Organ transplantation is probably the most successful option out there. And with current immunosuppression strategies, people can get 5, 10, 15, even 20 years, say, off of a transplanted heart. But the problem there is really one of supply. There's really just, not enough, people who've passed away to have transplant grade organs. And it's probably a good thing, right? It means we're living long lives. But there's still, tremendous need. And so the question is, how do we address that? So I think for probably the last 50 years, the goal has been, well, let's build a mechanical device that can, take over the function of the heart or the lungs or the liver. And there's options out there for some of those, but very few are basically permanent solutions. Probably the best case would be kidney dialysis, but that still involves basically being hooked up to a machine for 4 hours a day, at least 3 days a week to get your blood, cleaned up. So we really need better solutions all the way around. So the goal of a bioengineered organ is really to use advanced manufacturing and fabrication technologies, not to build with plastic or metal, but to actually build with living cells and tissues and tissue components, and to do that in a way where we can actually recreate, say, a new heart or piece of a heart or a new lung or liver and so on. So I think that was science fiction. What you're seeing today is, I think, the transition with really just the advance of new technologies of making that into reality. So there's still a lot to be done, but I think what was possible with some kinds of advanced manufacturing, say for metals, which now you have 3D printed fuel injectors, made out of titanium alloys that are in jet engines flying you around, that are work better, more efficient, a lighter weight. We're going to see that transition now into these new areas that previously we haven't been able to have that many really tools with in terms of manufacturing, but that's changing.
All right. So what's the focus? Which organs do you think would be the easiest to make? And then, where's it going to go from there? I've done some interviews with people that are making organoids, pseudo organs that approximate some of the functions or have some of the functions of organs. But, what you're talking about sounds like a lot more ambitious. So what's the first focus?
Yeah, so, like organoids are basically little tiny organ-like things in a dish, but they're really just fancy balls of cells. But they're very valuable because they allow us to basically do pharmaceutical testing on human-like tissues in a dish. So the low-hanging fruit for this technology in terms of bioengineered organs is actually similar to organoids, but like one additional level of sophistication. And what that means is, if you have a drug that might negatively affect, say, the heart and cause an arrhythmia, and arrhythmia is basically where the heart doesn't contract correctly. Instead of being synchronous and in a rhythmic beat, it actually just kind of fluctuates and can't actually contract. Some of the effects of drugs actually don't manifest until you have a certain size of tissue, right? Meaning you have an electric signal that has to propagate through the heart, and sometimes it has to come back around and hit where it started in order to start to generate an arrhythmia. And that is a function of both the tissue, but also the size of the tissue. And so kind of the lowest hanging fruit is basically, in a way, better organoids, or another way to think about it is like a more sophisticated and physiologic piece of tissue in the dish that can predict, say, that aspect of a drug's toxicity. So organoids will hit probably maybe, I don't know, I'm just, rough estimate, but say organoids can handle about 60 to 70% of the kinds of interactions you would have, but you need a more sophisticated system to do the rest of those interactions. So that's where bioengineered organs can have an immediate impact. The kind of the next level after that is going into people, but it's not trying to, say, 3D print an entire heart. It's actually trying to print a scaffold of extracellular matrix, say collagen and other proteins or other materials that are implanted. And you don't actually implant cells with that scaffold. You implant the scaffold, and it's designed to recruit cells from inside your own body to enhance your body's existing regenerative capacity. So you could think about that for healing bone defects that are larger than your body can normally heal, or muscle injury from, say, like a traumatic injury, like a car accident. When those are too large for your body to heal, you can create a scaffold to augment that and accelerate that and improve that process. It's also a lot better from like a regulatory standpoint, meaning the FDA's regulation on a 3D printed tissue or organ is going to scale. The challenge of regulating that and the time to get it into market will scale with the complexity. And so putting something in that doesn't have cells is also quicker to get into patients and have a major impact on the quality of life and your ability to get back to normal activities much more rapidly. Kind of the third generation of the technology is actually this grand vision of 3D printing a functional tissue or organ where you would actually replace the damaged either part of an organ or entire organ in the human body. That is still going to be measured in decades to get there because we have a lot of advances to make on multiple fronts, from the stem cells to the manufacturing and 3D bioprinting that I do, as well as just the time to get this through a normal regulatory process, meaning getting it through the FDA with all the different stages of validation you have to do to get there.
Wow, I didn't realize it's still so far away. So, where are you at today?
For some applications, right?
Some of the challenges.
Yeah, I mean, we are working on we have a range of projects, right, that we're working on. We are working on a 3D bioprinted heart. That's really, one of the more ambitious goals to replace, damaged heart tissue. It's very complicated, but we also have a lot more simple projects that are more near-term to translation. So we have a tissue-engineered cornea as an alternative to corneal transplantation that is already in pretty advanced testing in a preclinical model. We recently got funding from the FDA, so the Food and Drug Administration, to basically develop improved advanced manufacturing or 3D bioprinting technologies that can be used for creating implants. And we're doing that in a model of volumetric muscle loss, which is basically what happens when you have a traumatic injury. So that could either be, say, like a car accident where you lose a large piece of muscle. Also applies to our soldiers that may be exposed to an improvised explosive device or other traumatic injury. But the idea is to print a 3D print a collagen scaffold with certain kinds of growth factors that when you put it into the body is able to recruit your own cells to regenerate that tissue. And that's kind of cool for two reasons. One is we can 3D print these scaffolds, which means, we can match the structure and size and shape of that scaffold to the unique wound in each individual patient, because we can do, say, an MRI scan, and so kind of do this patient specificity. And then the second part is because we're only implanting materials that kind of accelerate and improve and augment regeneration, there's no chance for immune rejection, because immune rejection is pretty much driven by putting in someone else's cells. So we don't have that problem either. And so, these are technologies that, are going to be realistic in the marketplace in this 5 to 10 year time frame.
Okay. And then of the organs, I would think, again, some are much more simple than others. Like a kidney is probably one of the most complex with a lot of different types of cells, but maybe a smooth muscle or, like a bladder or skin would be a lot simpler. I don't know. Is there a hierarchy of organs that when they are 3D printed, which ones the first ones will be?
Yeah, I mean, to your point, there are organs with varying degrees of complexity, types of cells, and how hard it is to even get those cells. Also, how much vasculature they require. So, blood vessels from large arteries all the way down to small capillaries are really important for, basically enabling these tissues to survive, just like they are in our own tissues. And so those still remain challenges to fabricate. So wherever you have less of that, the better. So in our work in the cornea actually doesn't have any blood vessels. That's why it's transparent and you can see through it. So for us, that's kind of a lower hanging fruit and a more rapid path to translation, whereas the heart is actually the most densely vascularized tissue in our entire body because it's always beating and needs tons and tons of energy to do that, and tons of blood flow. So, there's this transition and kind of definitely spectrum of challenges in terms of where we can get first. That's one reason actually my lab, a lot of our technology, not all of it, but a good chunk of it, we release as open source. And that's in part so that we can provide tools and capability to other research labs to work on these various tissues and organs because, we're just one lab or we're just one institution, and there's only so much we can do, right? And so really trying to provide a kind of a foundation for other people to build off of in different directions is also part of what we try to make happen.
So in creating organs, what are some of the biggest challenges? I've heard like vascularization is really tough and it's hard to get it to go beyond. I don't know what the scale is, but even if a part of the body or cells are more than a millimeter away from a blood source, they can't function, they die.
Right. Yeah, that remains a challenge to the entire field of tissue engineering, which is basically, building tissue, whether you 3D print it or use another technique. And that still remains. We're actually been working through some pretty major advances in that area. I'm aware of a few other labs that are as well. And it's really leveraging the ability to 3D print to create that vasculature for you in ways that we could not do previously. This is something that will be solved. We're kind of in the process of solving it. It's hard to put exact numbers on it. It's probably going to be sooner for tissues that have less vasculature and harder and longer for tissues that have more vasculature. So, cartilage is a good example of a tissue that has almost no vasculature in it, kind of like the cornea. It's white, whereas, obviously muscle is very dense with vasculature, which is why it has the darker color, in part. So those are real challenges. We take a unique approach to it, or not entirely unique, but somewhat unique, in that your body's own cells are really good at building capillaries. There's a process that's called angiogenesis, which is just how your body normally forms new blood vessels. So as you know, like if you go to the gym and work out a lot, your muscles get bigger, right? There's literally more volume to the muscle. That muscle needs more blood vessels, and the way that happens is as you generate new muscle cells, you also generate new blood vessels. So what we try to do is rely on the endothelial cells, which are the cells that normally line your blood vessels. They can form new capillaries from about 10 microns to about 100 microns in size. And then we're trying to use 3D printing to build a larger scale vasculature than that. So from 100 microns up to, say, 5 or 6 millimeters in diameter. So it's really trying to let the body do what it does really well, which is build kind of capillary scale vasculature, and then use the 3D printing to build a larger scale vasculature, which our body is actually really not good at doing. And so it's really trying to leverage, for bioprinting for what it does best, and then endothelial cells and your body's own methodology for growing vasculature to do that the best it can, and merging that. So it's easy to say that. It's a lot harder to execute that, and that's a lot of what the research is right now, making that kind of that vision, that process work.
Yeah. So, what makes the vascularization so difficult when it's tried by without using the body's cells to do it themselves? Like, why is this such a challenge?
Yeah, the challenge with vascularization is first of all, how do you build a 3D network of tubes within a volume of tissue that goes from really big to really small? It's like a branching network. So if you just think about like a tree, right, where you've got the trunk and it branches and branches and branches again. But once you get to the smallest little branches, it all has to then do the reverse and go from those tiny branches, back to another trunk. So it's almost like taking two trees and putting them like, top to top, right, so that they all merge at that capillary or smallest scale. That's proved really hard, to build it. It's also really prone to clotting, right? Your body's really good at trying to basically prevent, bleeding out. And so you've got all these factors in your blood that clot almost immediately when the blood touches a foreign surface. And so the way your body solves that is it lines all of your blood vessels with these endothelial cells. And these little endothelial cells, they spread out, create a really smooth layer inside all your blood vessels, and they secrete a wide range of factors that stop clotting from happening. And then when you get a cut or some other damage, those endothelial cells break down, and then you'll clot there. So when we build these networks, it becomes really hard to re-endothelialize them and make them so that you don't get clotting. That's really fundamentally the reason a lot of this doesn't work to date.
Well, actually, it brings up an interesting question. So in the human body, what's the size difference between the biggest vessels and the smallest ones, and how does it progress? Are there like discrete diameters of vessels in our body, and they step down in a discrete way, or is it just continuous? I'm sure that makes it probably harder to do if it is.
So largely you have kind of discrete changes in diameter that occur with like a bifurcation, right? So when a vessel splits in two, those two daughter vessels will be smaller in diameter. But the whole thing is designed, right, so that you can maintain proper blood flow as you get smaller and smaller vessels. One of the challenges is, and the blood vessels do scale in size from the smallest capillaries that can get down to, say, 8 microns in diameter. So even smaller than a blood cell, a red blood cell actually will deform itself to get through the smallest channels, all the way up to our large arteries that could be 3 centimeters in diameter, right? Which is, 3 centimeters, right, is 30 millimeters. So like basically 30,000 microns down to 8 microns in diameter, right? So that's the scaling we're talking about. So the one thing is to think about, well, how did that ever form to begin with, and why can our body not grow all those again in an adult? And the reason is that all these larger vessels started out, during embryonic development as very small vessels, and they basically grew into their size over a developmental process. And the things that happen during embryonic growth and fetal growth, a lot of those things don't occur in the adult human. They're basically shut off, and the different way of growing. So in the adult, we still have this ability to do angiogenesis. So, we can, if we eat too much and we get fat, we can grow new vasculature for the fat tissue, or if we go and work out instead, we can, get the new vasculature for the muscle tissue. But growing, say, like a new artery that's large diameter, our body has no way currently of doing that. And so that does require either an implant of some kind or a scaffold for trying to regenerate it, or implanting an engineered engineered artery from outside the body, for example.
So, if vessels go from 30,000 microns down to 8, but again, you've observed they step downwards in discrete increments, or is it continuous? Do you find vessels that are 29,400 microns, or do you only see, let's say, 30,000, 25,000, 20,000, 15, have we seen that in the body?
Yeah, I understand. Yeah, so vessels do come in all diameters, and, if you look around at the population in general, you're going to basically see probably vessels at every size. Where they do kind of change in a discrete way is just where you have like a split in the vessel, right? So, if a large artery splits in two, those two pieces it splits into will be smaller by a discrete kind of step down. But in general, a ratio. Arteries, though, can exist in a wide range of diameters. There's not anything set. And like the aorta in my body is going to be different slightly in size than the one in yours, and so on. So there's a normal, distribution within the population. So, when we think about creating an engineered tissue or organ, it's not just creating that tissue or organ too. It is also trying to get it to be the right size and shape to fit into each individual, right? So, even in transplantation, where someone may get a heart transplant, as you could imagine, some of the criteria for whether you get that transplant is not just matching the cells to make sure that the immune rejection will be minimal. It's actually making sure the heart is the right size to fit in your body. It can't be too big to fit within your body. If you're, say, a child versus an adult, obviously the child can have a hard time taking a transplant from an adult.
Right.
But also, vice versa, the adult cannot have, God forbid, a child heart transplant, because it wouldn't be able to handle the load either for the larger body. Huh. So you have to match the performance and size of the organ to the person you're going to put it into. If we can manufacture these directly, then we actually have the opportunity to not just kind of match them the best we can, which is what happens now with transplant. We can actually optimally match them and design them specifically for maximum performance and hopefully lifetime within that patient. And so that's some of what you get out of making this into a manufacturing process, which is what we hope to do, is this kind of control over what you're building.
Yeah, I just saw the movie The Grinch, so I was going to say this disabuses the myth of the Grinch having a heart 2 sizes too small. But anyway, it's rare you get to make jokes in this industry. But it makes sense now. I see why. So an organ that has a lot of vascularization, you have to deal with making sure the vessels are in all the right spots near the tissue it needs to be, that they split properly, that they're sized properly. I mean, it's very complicated, it sounds like.
Yeah, we have some ways of dealing with that. So there's great mathematical tools for simulation of these organs, but also, the imaging technologies we have, say, take an MRI image of an organ, we can get a lot of the structural information out of that. And what helps with things like 3D printing is we can actually take an MRI image of, say, an organ, and we can get that into the computer and turn that into a 3D model, and then we can use that model to actually fabricate the organ we want to. So that's some of the interesting things that we can do with these technologies. It's basically an entire digital fabrication process, because the MRI image creates a digital file that we use a computer to turn into an actual CAD file, and then we can use a 3D printer, which is basically a digital manufacturing platform, right? It moves a robot around in 3 dimensions and deposits material precisely in 3D space. And so that's some of the stuff that we start to be able to do with these technologies, and that's one reason I think we're accelerating now in what we're able to do, and we'll continue to accelerate, what we're able to achieve as more resources are poured into this area, as there's more research and development done, and also as there's more innovation, say, in both MRI imaging and stem cell science and surgical technique. These are all the things that need to come together to ultimately get this into patients where it's a viable therapy.
Okay. Yeah, I mean, it's a big challenge, but I'm glad you're up to it. So, okay, so what's the best way for listeners to learn more and to maybe interact or contact, CMU or your lab?
Yeah, sure. I mean, my lab is at regeneratebiomaterials.com. We're also on Twitter at regenbio. We also have the Bioengineered Organs Initiative at Carnegie Mellon University. So this is more of a larger umbrella effort to leverage expertise, not just from my lab, but from a wide range of labs that do robotics, that do manufacturing, that do biology, that do advanced imaging, that work in the heart as well as the lung, the liver, and other organ systems. We're rapidly growing that effort. You can get to that. I think you already have the website for that. I don't remember the exact URL off the top of my head. And then we also, go ahead.
I'll just say for listeners, it's engineering.cmu.edu/organs/index.html.
Perfect. We also have the Manufacturing Futures Initiative, which is, a broader, not so much in the bioengineering space, but actually in the broader advanced manufacturing space, to create new manufacturing technologies like 3D printing and so on that allow us to just basically build things we were never able to build before. And that's funding research in my lab and other labs in the 3D bioprinting, as well as other kind of new technologies. So one of the cool things we're doing there is not printing tissue, but we're printing soft rubbers and liquid metals together to create these wearable devices. So we can basically print custom wearable for any part of the body that can integrate sensors and the wiring and the electronic components for measuring things like movement and pressure and blood flow for various applications for patient monitoring. So again, medical applications, but leveraging other kinds of materials and capabilities. But again, that falls under the this Manufacturing Futures Initiative. So
okay, well, very good, Adam. You're involved in tons of amazing things, and I really appreciate you sharing your knowledge on the podcast. Thank you.
Yeah, thanks. Appreciate you having me on, and have a great day.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.